I want to begin our discussion on three-dimensional vectors, and what I've set up here is a vector. You can see this white vector coming along this direction. So imagine this white piece of string represents a vector, and it's got a length along here, and I'm going to terminate the vector up there at that piece of masking tape. And then I've set up some meter sticks, so you'll see the x-axis is here, coming along in this direction. So I've labeled that X, but I'm going to take this label away. And then the Y-axis comes in this direction. Okay, and you can see the Y-axis labeled. So these meter sticks represent the X and the Y-axis. And then this meter stick here represents the Z-axis. So this vector has three dimensions. It's going to have an X, Y, and a Z component. Now what we're interested in discovering is, how do I figure out what that X, Y, and Z component is? Now keep in mind what you're seeing here is, here's the vector along the white line, and then this red line here represents a line that goes exactly vertical, so it's parallel to the Z-axis, exactly vertical down to the XY plane. So this tabletop is the XY plane. And then this green line here represents the shadow, if you will, of this vector placed onto the XY plane. This is called the projection of the vector onto the XY plane. And this would be the Z component of the vector, because it starts at the XY plane, which means that Z is equal to 0 here, and then it goes up until this Z point right here. All right, so in our discussions, we've already talked a little bit about this angle right in here. And this angle is what we labeled theta. This is the angle between the positive Z-axis and the vector itself. And that's the angle theta. How might you find the angle theta? One way you could do that, since this is theta and that's along the Z-axis, by alternate interior angles, this is also theta. We can see that the tangent of theta is equal to this opposite side, the projection onto the XY plane, divided by the Z component, opposite over adjacent. Or we could say that the cosine of theta was the Z component here divided by the hypotenuse, which is the magnitude of the entire vector. So that would be a couple of different ways that you might find the angle theta. Now, this component in here, this projection onto the XY plane, it's going to have an X component, and the X component will run parallel to the Y-axis, perpendicular to the X-axis. So this would be perpendicular like here. So this component, this value, whatever it might be, that's going to tell us what the X component of this vector is. And then I can find the Y component by drawing a line from here over to the Y-axis. This ruler is now parallel to the X-axis. So this value here is going to be the Y component of this vector. So let me put the ruler back over here for a second. If I'm measuring from the X-axis, then this distance here is the same as the Y component. And this distance along here, along the X-axis, is the X component. This is along the Y-axis, or at least parallel to the Y-axis. So the angle in here we refer to as phi, the Greek letter phi. And that angle has a tangent equal to the Y component over the X component. And so the tangent of phi is equal to the Y component over the X component of this vector. And that's a three-dimensional vector and how we'll break it down. One other thing to think about, and this will become very important later on in one of the labs, we'll have a string just like this one in 3 dimensions. And if I take a piece of graph paper and put it behind the string, which I don't have a piece of graph paper to do that with, the slope of this line will equal the tangent of this angle. And the tangent of that angle, well, the slope of that line is the tangent of that angle, so if I can figure out what this angle is, what's left over from 90 degrees is going to be my theta. So this is the complement of theta. Remember, the complement of an angle is the piece of the angle left after you subtract it from 90 degrees. So the complement of this angle is theta. So if I can find this angle, I know what theta is. And I can find my x, y, and z components from there. I need this length, which is the magnitude of the vector. I need theta, and I need phi. If I have all those things, I can find out what that vector's components are. Let's talk about the cross product of two vectors. What I've got for you here is a green vector coming up along in this direction, and a red vector coming up along in that direction. So there's two vectors. And what we're going to calculate out, or what we're going to identify, is green cross red. So green vector cross red vector. And we're going to use something called the right-hand rule for that. But one of the things we talked about when we talked about cross products earlier is we said that the cross product of two vectors is mutually perpendicular to both vectors. That is to say, the cross product, which is a vector, must be perpendicular to green and it must be perpendicular to red. Now, one thing you want to keep in mind is that here are two vectors in three-dimensional space. But two vectors will always fall on a plane. And what I mean by that is I can always take a flat surface and have both vectors touching that flat surface. So if I extend this piece of whiteboard infinitely out, the green and the red vector fall on that plane. They are on that plane. And so there's always another vector perpendicular to that plane. So it either comes out in this direction or into and through this plane. That's where that vector green cross red is going to point. So the question is, does it come out or does it go in? And to answer that question, I'm going to use what's referred to as the right-hand rule. And the right-hand rule says, and you start with your right-hand rule, point your hand in the direction of green, because that's the first vector, rotate it in the direction of red, and your thumb will point in the direction of green cross red. In this case, that's pointing out this way. And so the cross product, green cross red, comes out this way, perpendicular to red and perpendicular to green. So green cross red comes out in that direction. If I did red cross green, then it would point down in the opposite direction. Keep in mind, A cross B is negative of B cross A. Green cross red is negative of red cross green. That's how you use the right-hand rule to find the direction of a cross product of two three-dimensional vectors.